Similarly, if I have a val I, and it's some integer, you won't know what the integer is. But you could say, I'm going to just go ahead and copy and paste this in here, so you don't have to watch me type all this. And now what I'm doing here is I'm saying I want to match on the variable I. So whatever I is, and you can assume that this is much later in the code, if it's a 1, 3, 5, 7, or 9, go ahead and transform that into the string odd. And so I'll return that. And similarly, if it's 2, 4, 6, 8, 10, return even. And then in this one, if it's anything else in the world, return the string other. And since I'm returning values here, I'm returning string, string, string here and here. I actually should assign that to a variable here. So I'll say val res equals that match expression here. And because I made I 1 up there, it matches this pattern right here. And then res becomes odd, which is right there. And I show that for two reasons. One is to give you another idea of what the pattern matching can look like. And another is it leads me into this. If you don't care about all these other variables, like I say, this matches the numbers 1 through 10 right here. And then this matches every other Scala value in the world right there. And because I don't care about whatever that value is that's passed in, I just use that underscore and then I don't reference it over here. But if you did want to reference it, you give this thing a name, so you could call it default. And then I could say something like, you gave me a $sign default, exclamation mark. And then you don't see that there because I is currently 1, but let's make I equal to 11. Then we'll go back up here. And now you can see that I took the default here and I passed it into the right side of the expression. So I find it in the case here, and then we transform this value, again, the transformation symbol here, we transform that into this string, and I use this default value right there, which is 11. Okay, now what I want to do next, and this is kind of interesting because the Scala match expression is an awful lot of fun, and that's because there's so many things that you can do with it in terms of pattern matching. And for a course like this, the question becomes, well, when are you going to stop? Because if I show everything, I could go on for, at least an hour. So I just want to show a couple more things. The first thing I want to show here requires this class hierarchy. So what I've done is I've switched over to the Ammonite REPL so I could paste all of this in at one time. And so I start by creating this trait called a sentient being, which comes, of course, from the Star Trek world. And then I create an animal, which extends a sentient being. So a trait is like an interface in other languages. So this is an interface that doesn't define any methods or any variables or values. And then animal is kind of like sentient being. It doesn't define any fields. But now I do define some fields. So I say I create a dog, a case class dog, and it has one constructor parameter named name, and it extends animal. And then I create a case class here named person. It has two constructor parameters. One is name and the other one is age. And it extends sentient being. So keep that class hierarchy in mind as we go through the rest of this. So now what I want to do is come in here and I'm going to create a method that can take a sentient being. And let me just go ahead and start typing because I'm such a slow typer. So I'll say get info. So I'm going to take this input parameter and it's going to be a sentient being parameter. And I'm going to transform that into a string. So I say I want to match on whatever SB is. And we know that an SB, a sentient being, can be a person. So that's the first thing I'll try to match on. So a person has a name and an age. And then I'm going to transform that. And I will say that a person, I'm going to do a really unusual thing and put one more space right there. And then I'll transform this into a string. I'll say person name equals $name and age equals $age. So that's the first case of a person that I want to handle. And then the second case is going to be the dog case. So I'll say I want to take that as a dog, and a dog can have a name. And then I want to transform that dog. And I'm actually using 5 spaces just to line things up, just because I want to do that for this video. And then I'll transform this into this string here. So I'll say name equals $name there. Okay, and that can be the end of that function right there. So what's going on here is actually very cool Because this is a case class, both dog and person really are case classes, I can use them like this inside of this function. And what I'm doing right here is known as an extractor pattern. So a case class, and if you're not familiar with case classes, you'll want to check out my video on case classes. But a case class has something built into it called an unapply method. And that's used to extract parameters from the class. Some people call it deconstruct. I can't remember what the other word is, but anyway, it's called an extractor is kind of the term that you'll see. So because person is a case class, it has an unapply method, and that allows me to write code like this where I can pull or extract these values out of a person instance, name and age. And similarly, I can do the same thing for the dog here because it's also defined as a case class up here. Again, this is one of the really beautiful things about pattern matching is I can just say, I want to take a sentient being, which is the parent here, and then I want to match on its subtypes and then deal with the subtypes here. So I match on person. And now I should go ahead and finish this with an example, right? So say val d equals dog, and we will call this one Zeus. So now if I call get info and I pass in d on that one, you'll see that output here that comes from here. Similarly, I could say get info, and we could do that on a person. Gosh, I don't know how to do Walter Bishop from Fringe. Gosh, I don't know how old he was. I'd say 55. Hopefully not insulting him. But I'm calling get info on a person instance. And so when I do that, I get this result here. Again, there's another example of pattern matching, and this is specifically pattern matching with case classes and case classes that extend a hierarchy like this. One more thing I want to show in this video is one of my favorite things to do is to write recursive code, specifically write recursive code with pattern matching. What I'm going to do is write a sum algorithm for a list of integers. So I'm going to say I want to define a function named sum, and it's going to take a list of integers, and then I'm going to return this sum. So I'm going to say that it's going to return an int as well. So my variable name is x of s. I want to match, so I'm going to do x of s match. And then when you're writing recursive algorithms, the first thing I like to do is define the end condition because it's going to call itself. So when you receive a list, the way you typically match on the list is you'll say, when I get the nil element, which is the very last element in a list, and by this I mean a linked list, when you get this nil element for a sum algorithm, return 0. And that's because this is something called an identity value. The value 0 has no effect on a sum algorithm when you're summing numbers together. So if you can imagine going through a list of integers and then you get to this very last value, which is the nil, then return 0, it doesn't add anything to the sum. Technically it's called an identity value, and I was trying to think of a different term that I would use. So I always handle the end condition first when I'm writing a recursive algorithm. And then the next thing I would do here is I want to say, because I'm getting a list, I want to break that into its head and tail elements right there on the left side. And then I want to use those values on the right side here in my algorithm. So to create a sum, what you do is you say, I want to take the head element, which is the first element in the list, and then I want to add that to the sum of all remaining elements. And the tail is all those remaining elements. And that's actually the algorithm. That's the sum algorithm using recursive programming. And this isn't tail recursive. I need to be really specific about that. In the real world, you want to make this tail recursive. That takes a little bit more work, but I just want to show a simple algorithm here. I keep mentioning nil with a list. So the way a list works is it is a linked list. One way to create a list in Scala is like this. So you create these values like this. Let me get that out of the way there. So this is a list, and it's going to contain the elements 1, 2, and 3, and then the list ends with the nil element. That's just the way a list works. This goes way back to the Lisp programming language, LISP. So when I hit enter, oops, I'm sorry, I need to give that, let's see, list equals that. This will work a little bit better. Okay, so that creates a list, 1, 2, 3. And so this is actually the same if I had said list. I'll do something different here. I'll say A equals list of 1, 2, 3. This is exactly the same as that. This is just the LISP, Lisp way of doing things. And I show that because I want to show that a list in Scala with a list class ends with a nil element. So then I go back to my algorithm here, and that's where I write this first case here, or hopefully this first case makes more sense now. So you're saying when I get a list of integers, I want to match on that list of integers right here. And one case is when I get to the very end of the list as I'm marching through it. When I get to the end of the list, I'm going to hit this nil element. So that's this first case right here. So when I hit that nil, I want to return 0. Otherwise, I'm still somewhere inside of the list. I'm at the 1, 2, or 3, in which case I come to this head and tail and I match that. So you can imagine the first time you come through the sum algorithm, the head is going to be 1, this 1 here, and then the tail is going to be 2, 3, nil. So then on the right side of the expression, I say 1 plus the sum of 2, 3, nil. And then that calls sum again. So then we come back up here. And now x of s is going to be equal to 2, 3, and nil. So you come here, it doesn't match the first case. It comes down here. And because I'm working with 2, 3, nil, now the head is 2 and the tail is 3 and nil. So then I say sum of 2 plus 3 and nil. And then you go through that a couple of more times. And then finally, you'll hit that nil case where you get 0. And this is where the recursive algorithm unwinds. Now I can test my function like this. I could pass in that list. And you'll see that result is going to be 6. And to make this more clear, a little more clear, bear with me a few moments. I'm going to just add a print line here. And I'll just say nil for that one right there. And then we'll come down to this one. So that's the first case. And, whoops. It's kind of weird doing this in the REPL. I'm so used to an IDE. And then here I'm going to say print line. And I'm going to use an interpolated string. And I will say head equal $head. Tail equal $tail. And that should be good. Okay, sorry about that. I had a little problem with the Ammonite REPL, so I switched over to the default REPL. What I was doing here was, for the nil case, I'm doing these 2 lines of code here. I'm printing out the word nil, and then returning the value 0. And then for the head tail case, I'm printing out the head and tail values, and then doing what I was doing before. And so now when I do a sum, and I didn't bring my list over, but that's a list of 1, 2, 3, adding a little extra space there so you can see what's going on. What this does is give us a little debugging information. So you can see the first time sum is called, the head is 1 and the tail is a list of 2 and 3. Then what happens is that sum is called right here again. So the head is 1, and then the tail is passed in the sum, and the tail is list of 2 and 3. So then we come back up here to the start again. We come down through the loop, it matches here again. And then this time the head is 2, and then the tail over here is this list of 3. And then we come back up to sum again. So this time we come in here. If I said that wrong, I apologize. But then again, we come down to this matching statement here. The head is 3. The tail is a list of that. And actually, this is actually a nil. So that's the tail, which is passed in here. So sum is called again with this value, which is exactly the same as nil. So this time it matches, comes in here, matches the nil case. And you can see that's printed out right there. That returns the value 0. So now all of this unwinds, all of these calls right here unwind, and we end up with the sum being 6. For the purposes of this video, I'm trying to show a few different things here. First is how to write a function using a match expression. So I've shown that a couple of times, and in this case I'm writing a recursive algorithm, this sum function, using a match expression. And when you're working with a list, another thing I'm trying to show is that you can always break a list down into the nil case, which again is the last case in the list. So in the list I have here is exactly the same as 1, 2, 3, oops, nil, like that. So you can always break a list down into the nil element here as one case, and then the head and tail as a separate case. So that was the second thing I wanted to show. A third thing I wanted to show is that each case can have multiple lines as part of its algorithm. So I've done that there as well. And then again, this was a recursive algorithm. So I have the call to sum or the call back to itself right here. And then the last thing I'd like to mention here is I have a really big page here, and I put this in the first and second editions of the Scala cookbook, and I believe this came from the first edition. So this shows pretty much everything you can do with match expressions. So you can see from the table of contents over here that I break match expressions down into the different types of patterns that you can use. So technically, these are the names for the different patterns you can use inside of match expressions. So we have constant, variable, constructor, sequence, tuple, and type patterns. And so then if I scroll down here a little bit, you can see that what I do in this example here is I'm writing a function called echo what you gave me. And I wrote this for Scala 2, so I put a note here. In Scala 2, you can match on the any type. On Scala 3, you should use matchable instead. So I'm writing a function that takes an any and it returns a string. And so then I match on that type X. And you can see the syntax here in Scala 2 is a little different because we have the opening curly brace right there. And this shows constant patterns. So these are things you can match on with constants. So an integer is a constant, a Boolean here is a constant, a string, and even a nil are considered constants. And then I get into more patterns here. So these are sequence patterns in this section right here. You can match on tuples. So this is a 2-element tuple right here, and this would be a 3-element tuple there. You can match on constructor patterns, and I showed that in one of my examples earlier with the person and the dog, that as I was extracting fields. Then I show type patterns here, so you can match on the types here. And a nice thing about this is you can say, if I receive a string, give it the variable name s, and then I can refer to that s over here. And then similarly with an int, I call it I, and then I use the I over here, and so on for all these other types here. And finally, when we get down to the bottom, there's this wildcard pattern. And honestly, I can't remember all these patterns off the top of my head.
And that's one reason I created this page, so I'd have all these solutions in one place. In summary, these last lessons covered the Scala match expression, and I hope they've been helpful.